So my title is The Art of the Live Upgrade, and it's kind of a brain dump of everything I've been thinking about for the last N years. Do this? Ah, come on. It worked a minute ago. Oh, I know. Great, it stopped working. No, now it works. Okay. So Klarna was a small startup in Sweden back in 2005. I joined in 2008. So I've been with them for a decade now. I don't know how time flies that fast. So originally it was just one Erlang-based system. It's for online payments. The idea is that we're an intermediate between the customer and the merchant, making it simpler for both. Okay, making it simpler for both to buy. And you settle your payment later using any method you like: cards, bank transfers, invoices. We're now in many countries, including Germany and the UK and the US. We have millions of customers, and nowadays we don't have only Erlang anymore. We have many different systems, and we're now a bank, which also means that we have big requirements on traceability and isolation. So let me describe our system. We call it CRED because it was named after the original name of the company, Creditor.
Sorry, it's still hard to hear.
Okay.
You made me speak. Lean in very tall.
Yeah, okay. This one. Try this. And it was a big monolith, originally handling everything from receiving purchases and doing bookkeeping to serving the web interface, printing invoice PDFs, all in Erlang. These days, we have moved out several parts to separate services, but it's still a very important system. It went live in 2005. That's 14 years of 24/7 availability. We've never had any scheduled downtime ever. The system has never been down for more than about 2 hours consecutive, worst case. So it's not perfect. We're historically about 99.98% availability per year. And, well, according to us, there's still a lot to do because we want those 5 nines. So some vital stats here. It's approximately 1 million lines of Erlang code, not counting tests. It's divided into about 250 separate applications, of which maybe 20% are external open source applications. So we rely pretty heavily on open source. We write a lot of ours. That's close to 4,000 modules in the system, and we have about 60 developers. They're spread out over half a dozen teams. Over the years, we've had 200-something separate committers, different people working for us. And we have the Git history preserved all the way back to late 2004, when the first commits were made, and that's quite good to have, to be able to dive that deeply into the history of the system, figure out why something looks the way it does. All in all, there are about 140,000 commits in the system. We have a pretty complex CI pipeline, which we're pretty happy with these days, consisting of Git and Bitbucket, Jira, Jenkins, Docker, Ansible, AWS, RPMs, and Artifactory. So just to go through how our pipeline and branching model works, we have the master branch is the current live version, and we have a branch called stable, which will be the next master by fast forwarding. It's always safe to base your work on that or on the latest master. Developers branch off of that, and every branch must have a Jira ticket because we're a bank, so we need traceability on everything. Then when you push to Bitbucket, Jenkins will build and run all the test suites automatically. Then we have code reviews in Bitbucket. You need at least 2 approvals per branch, since we're a bank. And we have path-based ownership of the code, so any changes to a particular team's code must be approved also by somebody in that team. When a branch is ready, it gets merged and integration tested, and the stable branch moves forward. Pretty straightforward. Every evening, the current stable branch gets tagged as a release candidate, and then we throw all our system tests at it. It takes 4 or 5 hours. And we have a live-like test environment with multiple nodes and full-size test DB and simulated traffic and all of that. We collect performance graphs and see if something has changed radically. But if everything looks good in the morning, we'll typically deploy the release. So every day we push out between 2 and 12 tickets, depending on how busy it's been. So it's a pretty good turnaround. Most branches for developers tend to live only for a few days. If it's a big project, maybe a couple of weeks. But of course, sometimes the pipeline gets clogged and nothing at all gets released for a few days. Sneaky error can make it all the way into the integration testing or system testing, and then when you discover that, you need to fix it, because before you fix it, you can't release anything. But of course, that's what the testing is for, to find these obscurer things before they go live. And it might take no more than an hour or two to get a new ticket and pull request and build and all that to fix the integration. But the main cause of disruptions is typically small hiccups in AWS or Jenkins or Artifactory or Bitbucket. And one of those things can ruin a whole night's testing, and there's no release in the morning, and then it can take a couple of days before we get something out again. Sometimes we have time for a rerun and a release in the afternoon, and we really hope that we can speed this up even more so we can release maybe twice a day. But on the whole, we're pretty satisfied with this. It's a good pipeline. But we also need to be able to push out quick fixes and configuration changes. If there's an urgent problem discovered on live, it could be a bug that's got in there, but it could also be that the environment changed in some way and the code wasn't prepared for that. And to do that quickly, you need to be able to bypass the main release pipeline, but you still need the ticket, the review, stakeholder approval, passing build and test suites, separate change requests to live operations, because we're a bank. But after that, you deploy it as for any other upgrade. Also, any configuration change, even if it's just changing an IP address of something, needs to be documented as a change request ticket. So there's a lot of red tape, but with good tools, it only takes a few minutes to set all that up. And so it's not that much of a pain. And having all this traceability is actually nice for developers too. So if you can do it, because it's very nice to be able to, a couple of years later, look back at why something happened, why was this changed. But when you have a big system that's complicated, it's also important to try to keep your developers happy and productive, which means that you want to keep local compile times down as much as possible. We have a heavily parallel build with 4,000 modules, you can understand that. It's important to reduce the whole turnaround time of the pipeline, so we also have huge parallelization of all the test suites, because we have lots of tests. Good tool integration is very important to reduce all that manual clicking in various web interfaces, so that in as much as possible they pick up what all the other systems have been doing. So if you push a change to a branch, that's detected. It's also important to track, to have some sort of good system for code ownership. And we have divided up all our apps among the teams. That reduces the likelihood of strange merge conflicts when you want to push your stuff to live, because you typically know what your team is doing, and if somebody else wants to change your team's code, they come and ask you first. It also makes it easy to determine who gets to review what. Okay. And dividing your code base properly into applications make it much easier to add and remove whole code units. Just adding a whole new application or deleting an obsolete application, that's very satisfying. It's also important to find as many silly errors as you can as soon as possible, preferably at local build time when the developer is doing it, like doing XREF checks to find out that they didn't just export a misspelled function and so on. And then you discover that, if you discover that 2 hours later when you've run all the test suites, that sucks. So pick it up as soon as possible. Okay. So we have reshaped our system a fair bit over the years. So when we started, it was a very different time compared to now. We were on OTP 10, which I think was the second open source release back in 2005. Common test did not exist. Rebar did not exist. Dialyzer hardly existed. Cloud computing was unheard of, almost. Yaws was the obvious choice for a web server, or pretty much the only one. There were no really good database bindings, so why not pick Nisha? I mean, it was a startup anyway. Nobody knew that it was going to be big. Yeah. And nobody in-house really knew how OTP releases worked. That was sort of a dark art from inside Ericsson. We were on CVS and Subversion. In mid-2010, we switched to Git, and that helped a lot with merges. Before that, merging was a big pain. And we were using cruise control for automated build and test. And we made every mistake possible, I think, when it comes to structuring the code and so on. Some of those books were not written back then. But Erlang and OTP and the Beam VM have held up incredibly well because they've handled this enormous growth that we've had that nobody really expected or dreamt of. And Erlang has allowed us to just keep restructuring bit by bit without stopping anything, really. The original system had something like 10 applications. 2 of those were called MISC and Util. And by late 2011, we had gotten about 30 apps and about 100 developers, and that was also getting painful when it comes to code ownership. People were treading on each other's toes all the time. So we had this kind of a Cambrian explosion where we split the code up into 100 apps in a big bang thing, still without stopping anything. And this made it easy afterwards to start, from that point, adding and removing apps as the unit of functionality. And now we're up to about 250 apps. Other things we've been doing is splitting up bad supervision trees. So the apps we had when we started, some of those were doing way too many things in a single supervision tree, in a single application, with multiple unrelated processes. So we moved those out to new applications, having their own supervision, could be started and stopped independently. When we did that, some of the processes were easy to they were not that critical, so we could just stop them and then restart them under their new supervisors. But we had to do some trickery to actually move some critical processes from their current supervisor to a new supervisor without stopping anything. Anyhow, this splitting of the supervision, moving from a kind of a deep supervision tree to a much flatter hierarchy of things, made it much easier to think about the particular responsibilities of a particular app. We've worked a lot on reducing coupling. As I said, we did originally every mistake in the book. People were banging on their keyboards, and you got dependencies everywhere. So we've been splitting up header files. Small header files is good, big is bad, just to avoid useless recompiling whenever someone touches a header file. You want to parallelize the build as much as possible. We've split the applications into layers, and we have a tool that does an Xref-like checking of application dependencies so that an application in one layer is only supposed to call applications in the layer below it and no other applications. This is also quite useful for maintaining the structure of the code base. We might open source that someday, but it's kind of grotty internally. Another thing is that code which was only really intended for testing should not be part of the release. That often happened previously, that you found out that you found some stupid function where the comment said this is only for testing, and then you remove it and something crashes on live because it was actually using it. No. And adding more abstractions, the usual restricting knowledge to specific modules, and others have to go through the API, such as what's the representation of a particular data structure, or how is stuff stored in database tables. So I mean, we rarely do full abstract data types that strictly, but we try to keep it isolated. Maybe a single application is allowed to know how something looks, and everybody else has to ask it. And of course, we try to break out subsystems to external services now and then if they are really better off running on a separate machine somewhere, and in that case they might not need to run in Erlang at all. Okay, so live upgrades, how you do it. You deploy the code, you load it, and prov it. Okay. So I guess the question is, why don't you just stop the servers and restart them one at a time like most of the world is doing? Well, partly is because if you have a system that already is built in a particular way, it might be difficult. If you stop one node, that means that you need at least 2 other nodes still running to guarantee redundancy. If you need just one node running, then you're 1 power failure away from complete downtime. Now, these days you might not care if you have like a bunch of nodes in the cloud and you just bring them up and stop them as you like. That's cool. But if you're writing something like, or making something like a black box server for telecom or something, then it or you're making embedded systems or something like that, then it becomes a matter of economics. You can't ship 4 systems internally just because you need them for redundancy. Also, stopping and restarting a node can sometimes take a lot of time, depending on what it has to do when it starts up. And you might not want that long window where nodes are running different code. When you do a live upgrade, that can have much less impact on the system. In particular, it enables you to do small changes without stopping anything. You can do bug fixes or temporary workarounds if something crops up. You can insert missing logging or instrumentation when you need it. That's extremely useful. You see some weird behavior and you realize that it's probably in this piece of code and it's not logging everything it should be logging, so why not put some logging in there and do an upgrade and see if we can figure out what's happening. You can, when you want to migrate a service, you can do stuff like insert redirections of calls to switch to that new service, and then we do this kind of often, that you run something in shadow mode for a while just to verify that the new service seems to be behaving as it should, but it's not actually doing much. And then you start moving traffic, a small percentage at a time, to the new service until all of the load is going to the new service. Then you shut down the old service, and eventually you can remove the obsolete code. You can do all this by pushing out incremental changes. Now, for various reasons, we don't use OTP releases. I guess that a lot of you don't really know what OTP releases are, but it's a way of packaging a release. It was invented at Ericsson. And for historical reasons, in those days, releases were very specialized knowledge, even for us. And the documentation and tooling back then was really poor. Nobody really understood it. Nowadays, you have things like rebar 3, which supports packaging up a release and just deploying it. We may switch to that one day, but we're in no hurry because rehab seems to be working. Releases use a static list of modules to be loaded and what paths to add and so on when you deploy the new release. But what we're doing is detecting dynamically which modules have changed and what apps need to be added to the code path and so on. Originally, that detection was based on the beam file timestamps, but that's a bit unreliable sometimes. Nowadays, we're using the MD5 check when you use code and modify modules. Much better. We also have something like upgrade actions for doing things beyond just code upgrade, and you need to also apply some change to the system as part of the upgrade. And typically, we don't ever use this possibility to suspend certain gen servers during the upgrade. We just load it. Okay. So, just so everybody knows how Erlang code management actually works, I'm going to go through it fairly quickly. So, some of the fundamental design decisions of Erlang is that you're expected to have very long-running systems, typically like telecom switches that may be standing somewhere in a completely unmanned little house somewhere for years. Nobody touches them. You're supposed to be able to upgrade code without ever stopping the system. Unit of code delivery is modules, and you can have at most 2 concurrent versions of each module. And some of the main points there is that it assures you that you don't have any memory leaks as you keep loading new versions. And it assures you that you don't have any older code running than the next to last version. So no process out there is still running old code using old data formats or protocols. That can also be quite important. Okay, so when you load an Erlang module, the bean code gets loaded into the current slot. You have these 2 slots, the current code and the old code. And when processes perform qualified calls, that is, module name, colon, function name, they go to the current version always. And then you get a bunch of calling processes that are executing code in that version of the module. When you load a new version of the module, it atomically moves the one in the current version to the old slot. And all the old callers will keep running that code. And the new version gets loaded into the current code slot. So any new callers will use that new version. What happens to the old callers? They will terminate, they finish or crash. Or they migrate by doing a qualified tail call so that they don't leave any references behind. So when you want to load something again, you need to purge the old slot, and that kills any remaining processes that are still running the old code, if there are. So you do a purge, and then you can load the next version again. And then you keep doing this. Okay, pretty straightforward. So what are the possible ways to point to code? That's really only the current program point of a process, or other program points, earlier program points that are saved on the process's stack. These reference a specific internal point in a specific version of that module, so it's not possible to just redirect them to the new version, because that new version could be completely different internally due to compiler optimizations and stuff. So to migrate a process to the new code, you must perform a tail call, so you don't leave any pointers behind on the stack that reference the old version. And you must use the qualified or remote call, the syntax M colon F, so you jump to the new code. And anytime you have a long-running process, you should regularly go via such a call so that you know that you're checking for new versions. If you have a server loop, then you typically do this between handling requests. It can be noted that funds are enclosures. They're not code pointers, they're handled differently, and I don't really have time to go into the details here. Some other day. There is something called the code server, which is part of the sort of the standard library. It's just called code. It manages the code path, keeps track of what directories you can load code from. It tracks additional info about loaded modules, like the path from where you loaded the bean code. It lets you do stuff like sticky directories and modules, which are for preventing accidentally replacing system modules. And some other utility functions like looking up the application directories, checking for module name clashes, or what modules are modified on disk. So some of the basic code operations: load file. You just give a module name and it will search the code path. And it atomically will move any current code to the old slot. But it assumes that the old slot is purged before, and if it's not, it will fail. There is, on the other hand, the shell function that you might be used to, the one called L, and that will automatically purge first and then do the load. So if you're actually calling code load file, you might be surprised that it doesn't purge for you. You can also use load binary to explicitly say load this particular binary object, which contains bean code. And you got that from somewhere. It could be sent to you as a message from another node. It could be that you ran the compiler and got the binary object that you just want to load without going through disk. you provide a file name which is just metadata, but you can put the empty string that there if you have generated code. There's the purge call, and that will kill any processes that are still referencing the old code. There's also the soft purge, which will instead give up and return false if there still is some process. So you have two ways of doing this. And you can check if it's possible to purge, or you can just hard purge. Then there's the delete, which is not that often used. It moves the current code to the old slot. And that means that no new calls can be made to that module name, but any existing process will still be running that old code for a while. So to fully purge a module, you'll need to first purge to drop the existing old version, then delete, and then purge again. That'll clean it out completely from the system. There's also some functionality these days to modify modules. So the modified modules function will list all the loaded modules that have changed on disk. That's what we use. There's also the module status if you want to query the status of a particular module and find out if it's not loaded, modified, or removed. And what these do is that they compare the MD5 checksum of the code that's currently loaded with the corresponding checksum of the bean code on disk. And there are a couple of shorthands in the Erlang shell, the MM and LM for modified modules and load modified. This is code that we contributed, and it's available since OTP 20. On the other hand, you have the code primitives in the Erlang module. Those are low-level primitives with no knowledge about search paths or stickiness or applications, things like that. So, and the code server is built on top of these. So ordinarily you shouldn't be using them, but you can if you know what you're doing. Generally you shouldn't use them to change the state of loaded code, because that can make the code server lose track of what's actually loaded if you deleted a module and didn't tell the code server about it. On the other hand, they're faster because there's no server-process communication overhead. You don't need to talk to the code server. Some useful primitives are like loaded function, which will just list all loaded modules. You can poll to see if a particular module is loaded or not. It just says true or false. And that will tell you if the current slot is populated. It will not tell you about the old slot. There's another function with a different name for that, the check old code function. They're not so bad. That one is not that useful. And then there's the check process code, which can be used to check if a particular module is used by a particular process. That's kind of an expensive operation, so you can use it in an asynchronous mode to tell it to do its stuff and then send you a message when it's done, telling you the state. There's the preloaded function, which will give you a list of all the modules that are always preloaded into the beam as part of the beam bootstrapping. A new thing since OTP 19 is the atomic loading of multiple modules. So something that we've been hinting to the OTP team for several years, that this would really be a good thing, so we would take some credit for this. And one day they just said, hey, we've implemented this atomic loading. You want to have a look at it? Yes. So it means that you take a bunch of modules and you have all or nothing loading of them as a single operation, and it becomes visible as a single atomic operation. That avoids certain kinds of race conditions between modules, where, for instance, a newly loaded version of a module wants to call a new function in another module, but the new version of the other module hasn't even been loaded yet. And then the call will fail while you're still loading code. Stuff like that can happen. So we have the simple function, atomic load, and you just give it a list of modules to load. The loading can fail if one of the modules would contain an onload directive, for instance. Possibly some other cases as well. And if it fails, nothing has changed. Nothing has happened. But there's also a couple of functions to perform two-phase loading, where you first say prepare loading for these modules. And that does most of the hard work, but there are still no visible effects on the system. It's just prepared it in the background. And if you decide to not go through with it, it will just garbage collect the preparations. Nothing has happened. But if everything seems okay, then you say finish loading, and then all the modules just snap into place. That can also fail. Okay, a note on Beam code and Erlang VM compatibility is that you're generally guaranteed to be able to take Beam code that you compiled on a previous version and use it on the following versions, Erlang VM. That has sometimes not been true. Well, they didn't realize it in the testing in OTP. There was, for instance, an incompatibility between the fun representations between OTP 16 and 17, which caused a major headache for us when we tried to move. And recently, there was this dropped Beam support for the so-called tuple calls in OTP 21, but now that's been fixed by, there's a compatibility flag if you happen to have code like that, and you need to get it up and running before you can start recompiling stuff. Okay. Let's talk a bit about mindset when you're doing live code upgrades. First of all, you should expect failure now and then. You should do your best to get upgrades right, but don't trust that they will not go wrong occasionally. That will happen. So you should try to write resilient code that stays alive, survives minor hiccups, and logging is your friend. Also, don't scare your live ops people by sort of causing unnecessary bursts of errors, because sometimes you know that when you bring an upgrade live, it'll cause a short-lived flood of messages coming, and then everything's nice again. But if you didn't tell live ops about this, they'll go crazy and start following everybody. So at least add some kind of note to the upgrade that you know that this is going to happen. It's harmless. So when you're working with traditional software, there are some things that you need to think about when you're upgrading code. So if you're doing a cold start with an empty system, there's typically nothing to worry about. You don't have any local old data. But if you do a restart with a populated system and new code, then there could be old data representations stored on disk and so on, all of this. And of course, if you speak to other machines that have upgraded, they could be speaking older protocols. Okay. But when you're doing live upgrades, there are more things to think about. So you have all the traditional stuff, plus that you have old data formats could still be in flight, in RAM, being used. They could be stored in edge tables, they could be waiting in message queues, they could be just hidden in the server process state. So it's not always easy to know when it's completely safe to remove the code that handles the old formats. And sometimes you might need to perform some kind of upgrade action to, for instance, rewrite all the entries of an edge table. That might be the simplest way to do it. Another thing is that you need to sort of think about the possibility of getting systematic failure on all the nodes. It's usually hard to avoid that you need to upgrade code on all the nodes more or less at once, because if they're going to do a new kind of feature, they need to be able to cover it. But if a critical component crashes because of the same kind of bug on all of the nodes, then your system is down. They might hit that same bug within a very short time span, pretty much as soon as you do the upgrade. What you can do is, well, think about the possibility of this happening, of course, and maybe add feature switches to ensure that you just bring on the functionality on a couple of nodes to begin with, and so on. Also, there really is no rollback, right? You only roll forward. As soon as you do any non-trivial change, it will affect the system as soon as it goes live. So it can change the runtime state of processes, and arguments being passed around here and there, messages between processes, stored in queues. You could have immediately written some data to corrupted database file, you can't roll back. That will just make the code incapable of handling the new data. So what you can do is, of course, try to push a new change that fixes the problem. Maybe the first thing you do is some kind of quick fix to just work around the worst problem, then you figure out how to solve it properly later. But there's no real point in trying to make your tool chain support some kind of complicated rollback stuff, because it doesn't work and you're not going to use it. Okay. Techniques. You want sanity checks, of course, XREF checks and similar things to ensure that new version doesn't have a missing function. And it can be kind of specific to what your system is doing, so it's hard to give a full list here of things to think about. You probably want to try to separate releasing the code from activating code. You can put in feature switches where you ship the code, but it doesn't do anything unless you actually pull the switch. And or you can release in multiple phases where you first ship code that handles new data formats before they're actually being produced. When all that code is in place, then you ship the code that starts producing it and keep handling both versions for a transition period, and then eventually you delete the obsolete code that handles the old stuff. You want to separate the may crash code from the must not crash code. So for many subsystems or applications, it's completely allowed for them to just crash and restart. It doesn't kill the entire system. You just use your normal precautions for doing upgrades, but you assume that things can go wrong and you will get an application restart. And if the application keeps just restarting and restarting and restarting, you have to apply a fix and all is well again. But for some subsystems, they are critical to the node. If they go down, there's no point in having the node running anymore, because it could have lost track of stuff, and it's better to just shut it down and restart the whole node and hope that you have redundancy in other nodes. So for that kind of code, you need to know first which code it is, and you need to keep that code simple and obvious so that you can always see what it's doing as much as possible. If you have complex stuff, put it somewhere else in a separate application. And be conservative with changes. Don't go in there willy-nilly and do, oh, this will be cool, and ship it, and then you bring all the nodes down. Yeah. Sometimes you need to do some temporary dirty hacks. Typically stuff that you have some internal functionality, but you need it for an upgrade action, so you export it. If you do that, maybe you need to rethink its role, and maybe it should be part of the API or something. Or you just hide it away again. You can use things in OTP like the sys module and other internal functions to sneakily modify the state of a running gen server. That's occasionally useful when you want to do some really tricky modification of the code. And it's quite usual that you need to move stuff around on disk, so you need to put in soft links here and there. Just keep things running. Okay, full upgrade testing is very good to do as well. We have a part of the CI pipeline typically runs in Docker containers. So you can set up a small cluster. You don't just do it on one machine, but set up a small cluster with simulated load. It shouldn't be just idling, because if it's idling, then you're not actually testing what's happening in a real upgrade. In a real upgrade, there's processes doing work, and then you change the code. In an idle system, nothing is really happening, and then you change the code, and nothing is still happening. So you set up this system, and you start it on the current live version, and warm it up for a while with simulated traffic. Then you deploy your candidate release version and perform the upgrade, and see what happens. Collect error logs, preferably look at metrics. Some pitfalls. Remember to enable code migration. It's a common one. Most people with experience do this without thinking so much about it, but occasionally they miss it. So if you have any servers or just a long-running task, it should regularly go through one of these qualified tail calls, so it checks if there's new code to switch to. If it doesn't do that, it will be stuck in the old code until done or killed. And it's happened that you ship some code that's supposed to do some kind of like heavy job, maybe crunching a table, and then you realize that you started it off and it's not doing exactly what it's supposed to do, but it doesn't respond to code change either. So you either let it finish or you kill it in mid-execution. Yeah. It can be easy to miss this even in a code review. You also need to remember to update settings everywhere. So that's also a different thing from ordinary code upgrades. That in a live upgrade, you need to apply change settings. You need to apply them both to the running system and to whatever your representation on disk, your configuration files. Because otherwise, if you get a restart, it'll forget your new fancy setting. That's also easy to forget these things. So, some advantages and disadvantages. On the plus side, you have small impact on the running system. You can release often. And you can fix problems or add features without stopping anything. It's quite amazing, really. And you can gradually reshape the code. But it needs careful coding and knowledge that not everybody has. It takes time for when we get new people in, it takes them maybe a year or so before they really get their minds around this. And some changes must be released in phases and so on, which could be simpler if you're just doing a stop-start upgrade. Should you be doing it? Well, if not having to stop nodes is a major advantage to you, then yes, you should. But if you're happy with stopping nodes, it might not be worth it, except for quick fixes. Okay.